So this is going to be chapter 3 of your book. In the syllabus, it is chapter number 2, but then in the it is chapter number 3. So you can see the title. It's the reciprocal lattice and determination of crystal structure. We won't be actually doing the determination of crystal structure because, quite frankly, this is done only at the PhD level. Okay, but then what are all the backgrounds required for that? That will be discussed in this chapter. And the concept of reciprocal lattice is pretty tough. So please follow the class properly. So I'm going to start off with something that you have all studied from your school days, Bragg's law. You studied this, right?
In optics.
Have you heard of Bragg law?
Yeah.
Yeah. So even in so what happens is you all studied diffraction, and you know that the condition for diffraction. Okay, you will be able to see diffraction only when the size of the object is comparable, size of the object, or the gap between two objects, or the slit width is comparable with the lambda of the radiation used. Okay, so this is what you studied in optics. Now coming to X-ray, X-rays will have lambda of the order of nanometer. X-ray is also an electromagnetic radiation. It will have wavelength of the order of nanometer frequency wavelength. So what happens is if you are going to have objects which are at a distance of few nanometers away from each other, then you can see diffraction. Again, repeat, if the lambda of the electromagnetic radiation is closer to the size of the object or the distance between objects, then you can see diffraction. You know that in the case of crystals or any atomic structures, you know that the space between the atoms is of the order of nanometers. Therefore, what happens here is X-ray, when you allow it to hit crystals, the X-ray will not see it as a surface. When you allow the visible light to fall, visible light, I hope you all remember, the lambda will be few hundreds of nanometers. So what happens is it will not be able to, penetrate and look at the atoms. It will just see it as a continuous surface. But then when you allow X-ray to fall on the material, then what happens is it will be able to see these individual atoms sitting at the lattices. Okay, so let me just try to draw a picture here. Let's say this is my crystal. Okay, inside this crystal, I have millions of lattice points and atoms. And lattice directions, yesterday we discussed, right? The plane direction, the plane HKL parameters of the planes and all. So what happens is, first of all, if this is a material, it will be made up of a number of crystals or crystallites. You studied this SPM. Now, within each of these crystallites, what happens is you will find little crystals, the unit cells, or you will find atoms which are making different planes. There will be different planes, orientations of the planes, like for example, 100, 011 planes, 001 plane, 200, 002, 020, 211, 121, like that, different orientations of planes will be there. Okay, let's say you're going to allow X-ray to hit. When you allow X-ray to fall on this material, what happens is it's able to penetrate and go to each of these surfaces. And what it will see on the surface is a picture here. You can see that. Let us take one family of planes. Let's take one family of planes. Here I am only showing a row because it's a two-dimensional drawing. But then you must remember that it is actually a series of planes. And the distance between these planes is d. And they're all parallel planes, equidistant from each other. This much is clear to you?
Yes.
Right. So now let us think of X-rays coming and falling. The X-rays come and fall on these planes, and they get diffracted by these atoms. They get diffracted by these atoms. And what happens is the angle of incidence will be equal to the angle of reflection. So loss of reflection also will hold good. And what happens is, let us typically take just two rays. So these two rays, you can see, will have a path difference. This ray has traveled an extra distance here. It has traveled this extra distance shown by these two curly brackets. Okay, whereas the one which is here is traveling a lesser distance. So finally, when, let us say, it is going to reach some photographic plate. Okay, X-ray, you know that X-rays can darken photographic plates. So let's say you're placing a plate. So what happens is, when they hit the plate, they are going to have a path difference. Okay, so Bragg's law says that if the path difference between the two diffracted rays is 2d sine theta. What is d? D is the interplanar distance. Interplanar distance. This is for a family of parallel plates which are equidistant from each other. Then 2d sine theta, if it is going to be equal to an integral number of lambda, if the path difference is an integral number of lambdas, then what happens is, you will get a constructive interference, or you will be getting a diffraction maximum. Okay, so what is this theta? Theta is the angle of incidence. What is lambda? Lambda is the wavelength of the X-ray. What is D? D will be the
Distance between the
distance
parallel
between the
planes.
planes. And obviously, the distance between the planes, I am sure you studied this in SPM, that the distance between the planes has got something to do with HKL. Okay, therefore, the distance between the planes depends on what is the orientation. Okay, so D will be different. So what happens is, if X-ray comes and hits a surface, not all planes, not all families of planes will be able to obey this rule, 2d sine theta. And again, remember that when we are showing one particular picture, one family of planes. Now, similarly, you may have a family of planes which are like this. So the ray which is coming and hitting may be hitting at another angle theta. This theta will not be the same as that theta. But there also, if this 2d sine theta is going to be some multiple of lambda, then there will be constructive interference. So you have to remember that if I have a block of material and if I'm going to do this X-ray diffraction, then some of the families of planes will be satisfying this condition for the given direction of the wavelength and for the
For
given
that,
wavelength. So what happens is, you will be getting, for whichever planes will satisfy that condition, those planes will be able to give you a diffraction maxima. So what happens is, when you have an X-ray plate and if you're going to take these, what you will be getting will be some characteristic pictures, some characteristic images, which you can actually study and interpret and tell which are the planes which gave rise to this image. And from that, you can calculate and find out what is A, what is B, what to C for the given material, what is the structure of the material. Okay, so this is how X-ray diffraction works. Have you understood something that I said?
yes, yes.
Right. I planned to go much faster than this, but then when I heard that you don't know this, then I have to really go slow. Okay, so I think I will, instead of bothering about how much syllabus I am finishing, I will bother about how clearly you are understanding whatever I am telling. Would you prefer that?
Yes,
Because we are anyway at a higher level. This course is at a higher level than it should be for a BSc student. That's the reason why I am scared. Okay, so the next picture shows you, this is called a Lee photograph. Okay, so here, this is one technique of X-ray diffraction study, where what happens is, you just get dots. You get a pattern of dots. Are you able to see a pattern of dots?
yeah.
Yeah. And read what is given there. It is a photograph for a cadmium tellurium crystal, where the A value is 6.48 angstrom, and these dots have So the orientation is 111, and X-rays are incident normally on a 1-1 plane in the 1-1 direction of the crystal. Okay, and you are able to get some images. So this they would have back calculated and found out all this information from this series of dots that you are getting. Okay, is there some disturbance? Anil, Anil,
Yeah, ma'am.
how many classes have you attended so far, Anil?
Two classes, ma'am.
Are you sure? I have not seen you in any
Yes, ma'am.
class.
I will join, ma'am.
Huh? I have not seen you in
I
any
have
class.
joined, ma'am.
You better attend the classes because I am finding that you're not attending classes. I'm taking attendance.
Okay, ma'am.
I'm taking attendance. I don't know whether you have noticed in between the classes, I come out of my slides. That is to mark the attendance. Today, I'm just making it explicit. That's all. Okay, so better attend the class because the examination is going to be descriptive. There will be derivations. There will be a lot of things that you're asking. And Anil, just mute it. Okay, so now let us just start off this chapter. So what I just gave you was only the prelude to this particular chapter. So let's just start off the chapter. So X-ray diffraction is simply an experimental tool to determine the crystallographic structure of material. When we say crystallographic structure, we are talking of A, B, C parameters. We are talking of what are the angles alpha, beta, gamma that A, B, C will make with each other. Then we are also talking about whether it is BCC, FCC, all this information you can get from X-ray diffraction. And the diffraction pattern, as you have seen, will be a series of dots. And from the dots, you have to find out. And where are these dots coming? Each dot there corresponds to the diffraction maxima of a family. So you saw a lot of dots there. So please remember those dots are not coming from the same family. Each dot, this is important, each dot corresponds to the diffraction maxima of a family of parallel planes with a given orientation and common spacing. Like for example, I may be talking about 200. So all the 200s will be contributing to that single dot. Okay. Next, and similarly, there will be other dots which may be coming from other such planes. Next, okay. Now comes the logic. This is very important. A length in some proportion to the spacing between the families, between the planes, is represented as a point on the normal drawn to the plane. Okay, and the point is a representation of a family of planes. I'll explain what this means. If I'm talking about a family of planes like this, and the distance between them is DHKL. I'm putting HKL because HKL talks about the family. So I will say DHKL to talk about the gap between the planes. Okay, so now what happens is you must draw a normal. If you draw a normal to this, okay, and if you take one of the crystal lattice points as the origin, if you take one of the points here as the origin, then your X-ray diffraction, the point that it has given is actually a point on this perpendicular bisector. It is a point on the perpendicular bisector, and the location of this point from the origin is related to D. The location of this point from the origin is related to D. Okay? It is also related to the orientation. It is related to orientation that we need not specially say because it is lying on the normal. If it is the dot is lying on the normal, it definitely has something to do with the orientation. Then where exactly the dot lies, that is decided by the D value. Are you understanding this? It's a difficult concept to understand, but at least are you following what I'm saying?
Yes, ma'am.
Yeah. So that means a dot is going to represent a family of planes. So now you can ask, Madam, on that, can there be only one dot? Okay, let us say that this one dot is representing 100. Then you can have another family which is also having the same orientation, 200, 300. So are you able to see that I'm talking of different families here? But they are all parallel. 100 set of families are all parallel to each other, and the gap between them is some D100. 200 is also a parallel family, but then the gap between 200 planes is half of that between 100. Pujita will agree with me.
Huh?
You're Puja or Pujita?
Pujita.
Pujita. So Pujita, you will agree with me? The 200, the gap will be half of the
Yes,
gap
yes, yes,
between
yes, I
100.
will. Yes, I will.
That means that's a different family, but the
Yeah.
orientation is the same. So what happens is on this perpendicular bisector, you will have a series of dots which are coming from parallel families. Parallel families. There are three families I'm talking about here. They may all be parallel, but they are all different families. So these three families will give rise to three dots on this line. Is that clear?
Yes.
Each family is represented by one single dot. Okay. And where is the dot lying? Dot is lying on the perpendicular bisector to the planes. And the location, what is the logic of the location? I'll just explain. The distance of the point from the arbitrarily fixed origin. The distance of the point from the arbitrarily fixed origin at a lattice point. On a lattice point, you want to fix an origin. Okay. So the distance on the normal is found to be inversely proportional to the spacing between the planes. Listen carefully, it's a very, very important point. On the perpendicular bisector with an origin chosen as the one of the lattice points of the plane, you're drawing one normal, and then there will be a dot. That dot represents this entire family of parallel planes. So how do you decide that location? The location of the dot is going to be inversely proportional to the d value. Inversely proportional to the d value. So now let us go back to the previous picture. Like for example here, I can safely say that d value is the largest for 100 planes. So this will be representing 100 planes. Then the distance will be less for 200. So maybe I will say this represents 200. This d will be for 300, the distance will be still smaller. So a dot farther off will represent 300. Am I making sense now?
Yes.
Let us say 100, the d is 1 nanometer, just arbitrarily 1 nanometer. So what will be the distance for 200 planes? It will be half nanometer. So reciprocal of half is 2. So I'm saying double the distance. You put a dot for 200. Similarly, if I'm talking about the gap between 300 planes, it is 1 by 3. Reciprocal of 1 by 3 is 3. So I put the third dot. So the position, I am going to get a series of dots representing the various parallel families.
Ma'am, did you move to the next slide?
What is that?
Did you move to the next slide?
No, no.
Okay, okay. It
I'm
looked
not
like it
able to
was
see the
stuck.
slide. Oh, you're not able to see. One sec. Let me see. You're able to see now?
Yeah, now.
Okay. Now you're able to see this picture?
Yeah.
Right. Are you able to see three dots here?
Yes, yes, yes.
Three dots. So are you able to understand that the logic here is that the larger the d value, closer it will be to the origin on the normal. This is fine. So I can get actually a number of such dots on a straight line representing a series of families which are parallel. Okay, and the logic is that the location of the dots will be reciprocal to the spacing. Okay, or now what I am setting before you is called, because it's a series of dots that I'm getting, these collection of dots that I'm getting will be called the reciprocal lattice. They are called the reciprocal lattice. And please, I just talked about a family, three families which are parallel. Like this, many you can have, many orientations you will have. So these various orientations will give rise to different series of dots. Like for example, you may get a series of dots like this. You may get another series on the pattern. You may get another series of dots like this. From another set of parallel families, you may get dots like this. Okay, so you will get a group of such dots which form a pattern. Okay, now all these dots, a collection of these dots is called the reciprocal lattice. What is the real lattice? The real lattice is called space lattice. There the distances are in nanometers. Okay, but in reciprocal lattice, what happens is you are no longer talking in terms of distance, you are talking of the reciprocal of distance. So the dimension also will be reciprocal of length. So now from the actual space, you have moved to a new space called the reciprocal space. There you are getting some dots, a collection of dots. Now these dots are called reciprocal lattice. They are no longer your actual space lattice. They are not actually positions where your actual basis is sitting. Your reciprocal lattice is not your XYZ plane. They are X inverse, Y inverse, Z inverse planes actually. Okay, it's that space. And in that space, distances will not be in terms of nanometer. It will be inverse of nanometer. And every dot there is not talking about one atom or a basis. It is talking about a collection of parallel planes with equal distance. I hope you're understanding whatever I said. It's a very difficult concept. Many people who have been in the field for many years also don't get this clarity. So at this age, if you're able to get this clarity, that itself is, I would say, a big thumbs up. Because if you look at what is the objective of the course, when I share with you the handout, you will realize that one of the objectives is understanding this reciprocal lattice. Because it's a very complex, um, complex idea.
What's the use of reciprocal?
Yeah, that's what. Yeah, that's what is important. What is the use of omega? We talk about time. Time is real, but why do we talk about omega?
Frequency. Oh wait, omega. I thought you were talking about the reciprocal of time.
Why do you talk of frequency? Why do you talk of bandwidth? See, whenever you're doing any signal analysis, you're doing a Fourier transform, right? In mathematics, you must have studied.
Yeah.
Right. You're doing a Fourier transform and you're dealing with the, so when you're mixing signals, for example, you're actually, like for example, if I give you a complex waveform, I'll just give an example here. This is not at all syllabus, but I think it's worth discussing. Like for example, I have a signal like this. You should remember that this is actually made up of a number of sine or cosine waves. Sine and cosine waves, which are having slightly different omegas. I'm sure Fourier series and all you have done in mathematics, right?
Yeah.
So these ideas actually get into signal processing actually. That is where it comes. Or signal processing means you don't have to always think in terms of computer science or ECE. Even your mechanical disturbances, no? A loud noise that you get, for
I think
example.
it's something similar to this in spectroscopy.
Yeah, yeah. They are all related. Everything is related. Only thing is you may be talking in terms of different frequencies. That's all. Okay, so you can do an analysis. A sound is there, for example, or you are getting some pattern. You can actually analyze it and find out what are the component waves which came together and did got you this. And this analysis is possible only in the frequency space. If you have seen a Fourier transform mathematics, I hope you have used this. A Fourier transform of some signal, you will write it in terms of omega. Yes or no? You will be writing it as a function of omega, because you can do this mathematical analysis only when you talk in terms of omega. Similarly here, this is for time. Similarly, when you're talking in terms of space, okay, a Fourier transform of a space function will end up as a reciprocal of space, and that reciprocal of space is called the K space.
K space.
Do you remember K? K is equal to 2 pi by lambda you studied, right? So you'll be getting into K space. Okay. And most of the imaging that you're doing, the images that you you will get it in K space only. Like, for example, I showed you that Lee X-ray pattern. The patterns that you're getting, it's actually, you've got it in K space.
The dots.
Yes, that was K space. Similarly, MRI, you've heard of magnetic resonance imaging. That is completely on K space only. Those of you are interested, you can just go to the internet and just try to read that. Okay, and similarly, when we are talking about, I'll give you another example. We talk about band in SPM or even in chemistry, you must.
Hello.
Will be in K space only.
You got cut in between.
What is that?
You got cut in between.
Oh, you were not able to hear me?
Yeah.
Oh, so how many minutes? I don't know how many minutes.
No, just a few, like 10 seconds or so, not
Okay.
much.
So when it's actually the Fourier transformation that is required for analysis of space signals, or I mean, if I'm talking about space patterns like this, or time. Okay, in computer science and EC, you're dealing with time and frequencies. Here, when you talk to crystallography, when you come to crystallography, you will be talking in terms of actual space and K space. Are you able to see the analogy now? Okay, so you get, let's come to the third line here. You get a regular pattern on the X-ray film, which is a 2D mapping of a 3D structure. It's a 2D mapping of a 3D reciprocal lattice. Okay, so really what happens is, no, you will be getting a 3-dimensional series of dots in a space called K space. But what you see on the X-ray film is just a 2D of that. A 2D mapping is what you will get for a given direction of the X-ray. And this theta that you have incident X-ray like this. So you are able to see only some theta here, but then this theta will be different for the different families lying inside your crystal. So corresponding to different thetas, you will be able to see dots. Constructive interference. Okay, so now this series of dots that you got in a space called K space is called the reciprocal lattice. So now let's get into the analytical interpretation of that. You know that, electrostatic potential. You know that if you have a positive atom, you have a negative atom, you can talk about, or if I take a positive atom, for example, a positive ion, okay, all around it, there is a positive potential. An electron which is coming in the vicinity of that and this positive ion together will have a potential energy. You remember this? 1 by 4 pi epsilon naught q1 q2 by r. You remember this? Yeah. So what we do here is we can talk about the electrostatic potential for a periodic crystal. Please remember, X-ray diffraction is used to understand the crystallography of periodic crystals. If you don't have a periodic material, if let's say you take a glass which is amorphous, then you won't get any pattern. Okay, so if you take a periodic material, let's say the positive ion is sitting here. Okay, these series of dots are the positive ions, and let the spacing between them be A. So it's a repeating structure. And around the positive ion, there is going to be a potential energy whenever an electron comes into this space. This electron would be having some energy. And if you remember the formula 1 by 4 pi epsilon naught q1 q2 by r square by r, the potential energy will be negative when a positive ion and an electron are in the vicinity of each other. They come close, larger will be that negative potential energy. When they come far away, potential energy is less negative. And when they are really far away, the potential energy can become zero. Okay, so there is actually a 1 by r dependence. Okay, so as a result, what happens is you can actually draw a potential energy graph for each of these ions. For each of the positive ion sitting at the lattice, you can draw a shape of how the potential energy will be. Okay, so this is what is the graph. And because these ions are periodically located, you can actually get a series like this. And let us talk about a hypothetical one-dimensional crystal. There is nothing called a one-dimensional crystal, but let us imagine that I have a series of positive lattices, ions sitting at the lattice positions like this in one line, and the gap between them is A. Okay, it's a positive ion means electron, one or two electrons are out of it. So what happens if the electron comes close to this? It will have a potential energy. The electron will have a potential energy, electrostatic potential energy, that is going to be decided by the distance from the ion. Okay, and when it is out of bounds and here, the potential energy is zero. When it is here, potential energy is zero. So you can see that this potential energy of the electron is going to be, or rather the potential energy of this system is going to be periodic. It will be periodic in x. If I call this axis as the x-axis, then I can talk about the potential energy repeating itself, the potential energy structure repeating itself as I travel on this x-axis. As I travel on the x-axis. That's why you're getting a series of structures like this. Have I have I made you understand why these pictures are drawn? The periodic potential energy pictures, what they represent? The potential energy will be a function of x because this line is x-axis. The potential energy is going to be a function of x. So if I say this is my origin, at some x, I know that the potential energy is this. Now, at some distance x plus a, I will get the same potential energy. Are you following what I'm saying?
Yeah, like the potential is defined by.
Yes. The potential energy at a point is defined by u as a function of x, which is going to be equal to u of x plus t. What is t? T is translation vector that we have studied. T for a three-dimensional structure is n1a plus n2b plus n3c, we have seen. But this is a one-dimensional structure. So I can say that T translation vector is simply some m times a. What is a? A is the distance between the lattice points or the positive ions. Okay, so what I see here will be what I see here, will be what I see here, will be what I see here. Okay, so the potential energy keeps repeating itself for every A. or I'm going to see a periodic function. My potential energy is going to be given by a periodic function. Okay, so this is how the potential or potential energy would look for a crystal lattice, which is made up of identical atoms. Because the potential energy also depends on the atom. Okay, so it is going to be looking like this for a chain of identical atoms. We start off with one dimension. Later we can think of three dimension. Now is this picture clear to you?
Yes.
Right. Okay. So now U is a periodic function with periodicity A. Potential energy is a periodic function. Therefore, now comes your Fourier series. You can represent it as a Fourier series. You can write it as U of x is equal to some summation un exponential I 2 pi n x by A. This is mathematics. I'm not going to explain why this is so, because this has to come from your knowledge of mathematics. Okay, you can write it as a sum of series where each term is going to be some un exponential I 2 pi n x by A. The periodicity is coming from A. Okay, now what we'll do is we will simply club together some terms. We'll club together some terms. This 2 pi n by A, we will call it G. We will call it a vector G. Okay, we will call it a vector G. So G is going to be equal to 2 pi n by A. 2 pi n by A. And you can see it is having a dimension reciprocal of distance. Reciprocal of distance, and they were all on that normal plane. Okay, so you can call this also a vector. You can call G also a vector. Now this G has the name reciprocal lattice vector. A, B, C were called the space lattice vectors. Similarly, you can talk of G, which is reciprocal lattice vector, the gap between any two adjacent points in the reciprocal space. So that's your G. Now from here itself, you are able to see there is an n coming there. So n can take values 1, 2, 3, etc. So now what you will do is you are able to get a set of vectors. So A is a vector, G is also a vector. So you will get a set of vectors for different values of n. Okay, or you can see that my G's are going to be simply, if this is my origin, so this corresponds to n equal to 1. I get a point here. This is my vector corresponding to n equal to 1. This is my vector corresponding to G vector corresponding to n equal to 2. This is my vector corresponding to n equal to 3. Or I am going to get a one-dimensional collection of points which are equidistant. And what will be the repeat distance? The repeat distance will be 2 pi by A. 2 pi by A, if I go to the next. One more 2 pi by A, if I go to the next. One more 2 pi by A, I go to the next. Okay, so what you have studied here is, if I have a one-dimensional collection of lattice points which are having identical atoms and ions, I'll keep on, I won't specify ions and lattice, let's just take it as the same. Okay, so I have each atom or ion sitting at these lattice points. This is one dimension and the gap between them is A. Then the reciprocal lattice for this one-dimensional structure will be this, okay, and the gap between the lattice points will be what?
2 pi by A.
2 pi by A. 2 pi by A. This much you have understood, then a lot of headache is over. Guys, the two guys, I don't know whether you're following. Abhinav?
Yes, ma'am.
Are you following what I said?
Yes, ma'am.
Believe me, man, none of our teachers took care to bother to teach us like this. We understood as students, the difficulty of imagining this entire thing. That's the reason why I'm trying to spend more time for this part of the syllabus. Okay, so the set of 2 pi n by a where n equal to 1, 2, 3, etc. are called the reciprocal lattice vectors. So uh, these lattice points are located in a space called reciprocal space. Okay, now you know that u of x is periodic. That's what we started off saying. U of x is periodic. Therefore, exponential I g dot t has to be equal to 1. Only then the periodicity will be happening. Yes, the function will repeat itself for different values of n equal to 1, 2, 3. That means for every jump, exponential I g dot t should be equal to 1, where t is the m times a. Okay, some multiple of a. And again, care to notice that g dot t will have no unit. G is reciprocal of length, t is length, so g dot t will not have any unit. Okay, so exponential I g dot t equal to 1 has to necessarily be true for you to have the periodicity. This means that g dot t is an even multiple of pi, because you know that exponential I 2 pi n equal to 1. Okay, therefore g dot t should be an even multiple of pi. If this is true only, you will get that periodicity. Okay, so now let us go back. If you are talking about a three-dimensional structure, instead of writing a t, you will put a r, where r will be equal to some n1a plus n2b plus n3c. And similarly, G also will be three-dimensional. Okay, next, three-dimensional. So how do you write G? You will write G as some M1 A star plus M2 B star plus M3 C star. Go to the previous slide. There, I wrote G is equal to 2 pi n by A. 2 pi n by A. Instead, think of a three-dimensional structure where this is A, this is B, and this side is C. So corresponding to each of them, you should be able to get lattice points. Okay, so what happens is you will have three G's. Because it was just one single, we just wrote a G there. But then you may be having a 2 pi n by A, 2 pi n by B, 2 pi n by C, corresponding to A, B, C. Okay, therefore, in general, for a three-dimensional reciprocal lattice, you will write G is equal to M1 A star plus M2 B star plus M3 C star. Okay, now what are these A star, B star, and C star? This A star, B star, and C star are the edges of a primitive cell in a reciprocal lattice. Now we have gone to a different space called K space where you are having dots. So you can take these dots along three directions and make a cell. The edge of the cells will be A star, B star, C star. What is the relationship between A and A star? A and A star are related by this equation. A star equal to 2 pi by A. Similarly, B star equal to 2 pi by B. C star equal to 2 pi by C. Once more, I'll tell you, in your normal space lattice, let us say I have a structure like this with lattices or atoms sitting at the corners. Then, if this side is going to be A, if this side is B, and if this side is C, then in my reciprocal lattice, this will correspond to some structure with sides as A star, B star, and C star. Remember, A star, B star, and C star don't have the dimension of length. They have the dimension of reciprocal of length. And how did you get this A star, B star, and C star? You got A star, B star, and C star because of those reciprocal dots that you got, those lattices. And each of those lattice points represents a set of a family of parallel planes in the real space. Getting complex?
It's actually getting more simplified.
What is it? Pujita, can you repeat?
It's actually getting more simplified once you explain with the diagram.
Yeah, once I explained, once I explained. And you know something, I don't know, I enjoy teaching. When I read it, my understanding will be less. But when I explain, my own clarity improves. Okay, I am sure that in every batch there will be a few students who like to teach their classmates. Of course, now with the lockdown and all, it's not possible. But otherwise, I'm sure in your batch also there are some students who like to teach.
Yeah.
Why do they teach? They're not teaching you because they love to teach you. They will be teaching because their clarity improves. And with one teaching, that person does not have to prepare for the examination. That's the reason why they teach. Okay,
Yes.
I'm glad at least one person is saying that, it's becoming clearer. Okay, I'm glad. I think I'll stop here because for me, I was getting worried how I'm going to, because you're BSc students, how an MSc type of syllabus, how am I going to get it across to you? I was worried. Please, Abhinav, please go through this recording if you have not understood. Do you have a doubt, Abhinav?
Nothing as of now.
Nothing as of now. Okay, so I think we'll stop here. I prefer to go slow so that the concept is clear. After that, we can always, once it gets completely equations and all, no, there I can go fast. Okay, so I'll stop here.
Okay.
So good day, you can leave.
Thank you, ma'am.